Hello, welcome to a new video. I'm going to talk about using the SOP fluid nodes or the flip nodes. So if you're not really familiar with SOPs or flips, what are all these things? It's basically that now we are, for example, in an object layer, and often when I make something, I will drop down a geometry node and I will start building things here. So now we are in the geometry layer. So this is what is actually called SOPs, surface or geometry based manipulation. So with the new Houdini 19.5, we can now use fluid simulations inside of this geometry layer. So if we type in flip, we now have like the flip simulation options. So this is extremely useful. So otherwise, the previous methods would actually create a DOP network, which stands for dynamic operations. So we have to create a DOP, and then you can see here it switches to a dynamic layer where we can like put certain solvers and simulations and so on. So that's like the way it used to be for a while. So more and more things are going to this geometry layer, and that's what I want to talk about today is using the new flip or the fluid simulations in a geometry layer, because this is where I do most of my work. The SOP layer or geometry layer is like the best layer where you can find a lot of different things and do a lot of different aspects in Houdini. So let's start very basic and let's bring in a couple of nodes. So the first thing that we want to do is we're just going to type in flip again, and we're going to build a container. So this is basically now the area where the simulation is happening. So if I now would simulate something, it will only happen in this box. So that's step one. Then step two is then adding, for example, a solver. We can already plug in the solver. And if you type in solver, we can see we now have access to multiple solvers. So in our case, we want to use the flip solver. So we can also do pyro simulations, vellum simulations, rigid body simulations. You can see there are many solvers here now, which is really great to see. So we can now go to flip solver, and we can just plug in our dots over here like so. So by default, if I would now press play, you won't see anything because we have not assigned any water volume or fluid volume or something like that. So if we open here our panel on the side, if you press P, we can have some options. So the basic option we can do is, for example, add a water line. So if we just enable this, we should see like a water tank now. So this will here, if you look back at our box here, it will just fill this with water. So if I will now press play, we just have water that is really not moving or anything. Like there is some little deformation going on, but overall it's just a water line. We can have the position, we can have the height of this, so we can lower this or higher this, as you can see. You might need to then hit resimulate. We can also add some velocity and some other types. So this is like the basic thing you want to do is, for example, adding a water line. Now, after you do a simulation, in a moment I will come back and do some more interesting things. So after you do a certain simulation, you want to do a couple steps to make it into an actual more usable geometry. So we're going to use the fluid compression. So we're going to plug that in like so. So we'll see it will turn into these voxel spaces. And it will also need a particle fluid surface. So this will turn the particles into like a surface shape. So plug that in over here as well. And now this is actually like usable geometry. So this is roughly that process of setting up a basic simulation. Now let's make things a bit more interesting by adding a simple object to collide with, for example. Like what if I want to now have the test object, like the rubber toy? What if I want this rubber toy as a collider? So we're going to type in flip and we want to say add a collider, so add a collision object. So this will come between our tank and our solver. So we can plug the node in over here, and then the object that is now being created is a collision object. So we can now plug in our test geometry, and we can now here go back to our simulation and hit play. So you can see now it's sort of like seen as a collider. And because we have no extra data or motion set now, it doesn't do that much other than here like filling in like a gap for that object. So what we can do for now is we can just go to our solver and we can add a certain velocity. So here, let's say in the z-axis, let's add 5 velocity. So here, reset simulation, and now we start to see that we are sort of like colliding with the simulation. Now there are a couple things again you can play with. We can just place a transform here, and we can make this a bit bigger. We can also do a rotation of this. If I, for example, here would start to rotate this like so, maybe it's a bit more down in the water, like this. This is then more interesting, and then we can do a resimulate. And then we have another simulation like that. And if you want to look how the geometry looks like, we then have something like this. So we can see the water like going on top of the collision object. Now overall, like this is the most basic thing you can do. You can do like a simple water moving and colliding with something. If you want to like make this faster or have higher quality, we're gonna have to play around with the particle separation. So this is the default value. You will also find the default value here in the solver. So either you're gonna override this in the solver, or you can, for example, say, I would like to set the main value in the actual container where we have the simulation. So if we set this higher, the dots will be higher. So you can see like these simulation dots will be set to a higher amount. And of course, like this will run faster, but will have less detail. So if you are going to like your final steps to make something really cool, you can lower this a little bit to have like an extra detail going on. But if you're just like playing around, it's usually like better to maybe keep this as a lower value. And we can always afterwards start to merge things together like so. Like this. So again, we are using quite low quality results here. So if I would now go like a little bit lower, resimulate. So here the quality is a bit higher, as you can see. Again, we have like more details going on this shape. Then of course this is way nicer to use. We can also again play around with many different options here as well. We can also do a visualize option here, where we can just say like color using the velocity data, and then we have like some basic watercolors. So this is like example number one, quickly showing you how we can set up a very basic flip simulation. Now, what if we want to do something similar, but we want to have like a emitting source? We want to spawn objects that start to emit source. And I'm going to basically copy the system almost. I'm going to just reset the frames here for a moment. And we're going to just copy all the nodes. And what we want is we want to get rid of the collision. So we only have this basic simulation. And I'm going to reset my particles here back to the default value. So let's say we have now a sphere that is, for example, roughly here like this. Maybe it's a bit bigger, let's say 2. And this sphere is then spamming fluid, like this is an emitter that spams fluid. So we're going to have to go back to our flip nodes, and this time let's use the boundary node. So we're going to just merge that in over here. And here we have now a new geometry for sourcing. And we can just plug in our sphere like that. So by default, you should be able to see a conversion of this into voxels, as you can see. Like this is now a voxelized sphere. So if I now go back to my simulation and hit play, we should be able to see that this is now emitting a certain source for the simulation, as you can see. Like this is now what is happening. And we can make things a bit more interesting. You can also here remove the waterline. If you don't like this waterline, you can just disable this, play again, and now it will just bounce basically into nothing. What you can do is you can here also under collision add a ground and say ground plane. And now it will just like clash here with the ground. And of course it won't go out of the bounds of the container. So that's always important to remember. We can of course start to do interesting things by moving elements around. So let's say this sphere needs to move into a certain direction. So if I go to top view here, and let's, for example, move this sphere over here, and that's bringing a transform node. And we can now here rotate this. So we're going to use a little bit of expression, which is going to be called $F, which stands for get the frame number. So you can see it gets the current frame number and multiply this by, let's say, 2. So now if I would play the animation, my sphere is now just rotating like this. Make sure this is still in the container. So as you can see, I'm actually outside the container. So I'm going to just move my sphere inside the container. Otherwise, not much can happen. So I'm going to just make sure it's in the container. So now let's press play. And we can see that it's just now spamming that fluid like we see over here. So this was, for example, the original position, and it's now moving over time. So just to know that you can animate things over here, so you can have interesting effects. You can, of course, add multiple objects. They can add multiple spheres that sort of like spawn or emit fluid. And another interesting thing is adding velocity. What you can do is you can, for example, bring a point velocity node. So here we can add certain velocity data. So let's say we want to have some velocity upwards, or for example, on the x-axis, like some force in that direction. So the simulation will know what to do with this value. So as you can see, my simulation is going somewhat upwards, and now it's going downwards. And it's going to be mainly preferring this in the x-axis. As you can see, it's mainly going here in the x-axis, even though my sphere is just rotating around. You can see it's definitely going upwards, and it's in the x-axis. So in this case, I'm also like on the bound here of my cube. So if you want this to be bigger, you can of course make this bigger. So this is very useful to know and to play around with. For some users who are already a bit more advanced with Houdini or already know how to use some of these attributes and vegs, you can basically now create attributes defining velocity. So here I just added a look at a point 0 of the world. So using the look at, so I'm saying that get the current point and look at the center of the world, which is 0, 0, 0. And then I'm using that value here. So I save it in the normals to visualize here with the with these vectors, just quickly visualizing this. And I'm just saying that the normals multiplied by 5 is equal to my velocity. So what will happen now in my simulation? So if I now would reset, what will happen is my fluid will always sort of like be aimed towards the middle. It won't be perfect because we might need to play around then with the velocity amount, but it will always be aimed towards that middle. For example, here I can also enable the waterline, make sure the velocity is here set to 0, 0, 0. And let's play that animation. So you can see it will always be aimed towards the middle here. And because I now also also have a ground layer or a ground plane, my waterline needs to be actually also higher. So we can actually see the water line like this. So let's play this again. So we now have the proper simulation as I expect. So I'm going to quickly view top here. And as I said, it will always be aimed towards roughly that middle point, the look at direction. So this is just interesting to know that we can use normals or create our own velocity attributes just by code with vegs or something like that. There, of course, are nodes that you can use like point velocity, but in some cases you often want to make your own system to figure out the velocity value. So we can also now create multiple spheres, and each sphere has like another velocity direction, so you can have different ways of emitting that volume, for example. Now, with some of these basics out of the way, we can now combine some of the things that I just showed you. So what we can do is we can combine our collision with the sourcing node. So here is an example of, For example, our rubber toy being splashed on by some water. For example, like here you can see some of the fluid coming down, and it will just collide with that and splash out like this. So you can see you can start to combine it. And again, it's the same setup that we did before. So we're going to have our tank where we're going to simulate this. We then have our collision, which is then our rubber toy. We then have a source, which is then a simple sphere. We then have our solver, where we basically have almost no changes. It's just the default settings. And then we have our basic nodes here to do a meshing step of that. And then we have something like this. So this is just combining what I just showed you into like something that might be interesting or usable, or you can quickly just now replace the rubber toy with like, for example, like a glass, like you're pouring water into a glass or something. You can quickly input custom objects to collide with. So that's really interesting. Now, another cool example we can build is something like this. Sort of like putting some icing on a cupcake or something like that, like a cream. You can make this as well with the flip books. So you can see, well, it's a shape rotating in a spiral, and then it will just drop down into a shape like this. So how was this built? And it's built mainly with some of the things that I've already shown here. So again, we need to have a tank, and I just made sure it's like perfectly fitting on that size. Then we have mainly a sourcing volume that defines mainly the shape. And this is where the most interesting part is I just used the star shape to make a star. I did an extrusion of that. I did a remeshing of this. And after that, I made some more scaling and rotation options. Then I wanted to make sure that we have a way of rotating or animating this around a spiral. So first of all, we need to create a spiral, which can be done by just using the spiral node itself. And we can then just move this and rotate this into a better position if needed. And then I'm going to use the node called path deform. So this node will deform a object, which is the star shape, onto the spline spiral shape. And most importantly here is the offsetting position, which is then animated. So here, this is just animated. So how can we do animation in Houdini? You can just quickly right click and you can set keyframes. Once you start to make keyframes, you can open here a animator window. And here we can start to see our animation. So I can now grab these values, and as you can see, I can animate how fast this is going by just a simple curve. So these are some very, very basic animation editor options in Houdini. Once you set some keyframes, just open this editor and can play around with how this goes. So here I just animate this from frame 1 to roughly 40. So we have it like this. And then also here with then the flip source, you can see it just moves like this, like expected. And at a certain point, I stop spamming this, because this is also important to know, is that we don't need to constantly spam new fluid out of this shape. So under activation, this is where we're going to either enable or disable the current spamming of this. So what I did is I used a little expression. So we're going to get the frame number by saying $frame or $f. So this is getting the current frame number. And this should be smaller than 41. So as soon as we go too high in frames, we will return 0, which means activation is now 0, which means it won't spam anything more. So this is very useful to control. So everything below this will spam something, and this is then used into the solver, as you can see. So we have this shape now being created, and we then do the meshing step. So we have this interesting mesh. And also here, like, this is a simulation that took a bit longer, so I just cached this. I can definitely recommend caching out files, so you don't have to wait every time on them. So here again, this is then the simulation, like this. And then further, what we can do is just, for example, add a color. So this is just a gradient color. We can add also some ambient occlusion. So you can add some variation, and I do a color blending of them to just have some colors. This is just very quickly done, of course. You can do better if you add like a nice material. But this is then roughly the effect. And of course, the main thing that I also forgot is the viscosity settings. So you can just in the tank itself enable here viscosity, and you can put this to like a very large number, and then it will actually stick to each other instead of like splashing out. It will just like stick, because that is what viscosity is doing. We'll make sure that everything sticks a bit more in its original shape. As you can see, you can see the star shape roughly here. So it's roughly this setup, showing you some other elements you can do with this thing. Another interesting thing to talk about as well is we can use here the input of this flip container or tank. So this can be just like a simple box. You can just add a box over here. You can just, for example, add a simple box, and then in the box, this is then the simulation area. So you can just decide with this box how large the area should be, which is of course really useful. Now, the next step to this is that we, for example, have an animated object like this. So we just have this toy rotating around using here the frame numbers again, and just rotating that with a simple transform. Now, we can also now define a certain area around this. So we can calculate either the bounce shape. So this is just a simple bounce node. But we can also do a, for example, like a sphere. And we can make the sphere bigger by transforming this using the centroid. So you can fill in something like this, and we can just scale this larger. So like this. So this will now rotate with our object here. So if I now would grab this, you can see that my sphere is sticking around my rubber toy. And this is then my new bounce. And this is then my simulation area, so this circle. So here, if we go back to our simulation, so here I have a couple of frames of this simulating. So the starting frame is just like this. So we have our collision, which is the rubber toy. So you can see I added here that rubber toy. And that sphere is now here, my area where simulation happens. So over time, when we move around, you can see that we are only doing the simulation around our rubber toy. So this is extremely useful if you do many complicated simulations. We don't have to, for example, simulate like a whole big area. So if I would have a grid here, I don't necessarily have to create a simulation area that's like this size, because my rubber toy needs the whole size here. So I can define that we only have a specific area like this that is actually containing that simulation. So we can much more define where simulation is happening, as you can see over here. So, and then we do the normal meshing steps to get something like this. So this looks pretty cool. Then we can merge that back with our original shape or collider, and then we have something like this. So again, it's extremely useful to only have like a local bounce and say that this is where the simulation needs to happen, and we don't need to necessarily calculate something that happens here of the water, even though my simulation will later on pass to this area because it will just go in circles. And then one more thing that I want to show you here, and the reason why I like everything to come into this geometry network, is because we can now start to combine other elements of our geometry network. So we can start to generate procedural geometry and immediately feed it into like fluid solvers. But we can also use other solvers that we have already available. So we can use our rigid body solver to interact with our fluid solver roughly. So this is a quick demo of that. So here we have a pillar, and this ball is going to smash into the pillar and everything will fall in the water. So you can see this is now what is happening. So we have some interaction between that destruction and some of the water elements here. So of course I kept it quite subtle in the water, so we can see some of these elements clearly. So first step is I made a simple simulation of this pillar being destroyed. So if I go back here, so we have our pillar and our ball. If I press play, they just collide with each other and fall down. So if you're not familiar with this, quick rundown. We have a box. I made sure to set this on the plane here in the middle of the world. I did some bevel, I did some normal, and then I do a fracturing of pieces of this. So this is actually defining how it will break. Then I also need a ball shape, and I save this into a group so I can later add the velocity here. So once we have both of them, I usually convert this into packed geometry with the assemble node. So you can just enable here, create packed geometry. I really like to use this node. You don't necessarily have to. And then I'm also using that ball group that I made over here. And I'm using specifically add velocity data only to this ball group that is referencing to this sphere. And in this case, I'm adding a velocity of 20. So that's a higher amount. So once that is all set up, we just plug in a bullet solver. We're going to add a ground plane here as well. So under collision, ground plane. And I just increase the time a little bit so it goes a bit faster. And when I press play now, we have something like that. So you can play around with this and you can, for example, add more interesting fracturing details. Like this is like the most basic fracture you can have. So you can just play around with the values and have way more interesting fracturing. So this is step one, is for example creating this rigid body simulation, and step two would, for example, be again creating our fluid setup. So we just create a tank with fluid, controlled by a box in this case. Then we have a collision object, which is then our rigid body simulation. So this is the easiest way to just implement that, is to just have a collider object, and that will work. Then we will have our solver, and in this case we have a water line. And I'm also creating here a ground plane as well. So we can all quickly, for example, raise the water if you want to have more water. And then we just have to resimulate. And you can see now we are resimulating. So you can see our original simulation of the rigid body with now this water layer. And we can see this interaction going on with now this water. So you can see that this is pretty cool. And then we do our meshing step here quickly, and then we can just merge our results together. So we can merge the fluid with the rigid body, then we have something like that. So this is the basic setup here to combine some of the elements a bit more together. And again, you can cache things out if they take a bit longer to simulate. You can just cache things out. But from this point, you can also do like certain cold simulations interacting with water. You can do many things. And this is where I'm going to end the video. So I showed you some of these new SOP fluids that you can use. So everything comes now more and more into this SOP or geometry layer, which is really cool. So we can combine multiple elements of Houdini together in one network. So I hope you learned something. I hope you learned how to use some of these nodes to your advantage. And I hope to see you on the next one.